Dear students, let us start today the new chapter in coordination chemistry, crystal field theory. In this lecture, we are going to discuss assumptions of crystal field theory, application of crystal field theory to octahedral complexes, and distribution of electrons in strong and weak ligand field. Let us see assumptions of crystal field theory. Assumption number 1. In a complex, the transition metal ion is placed at the center and is surrounded by ligands with one lone pair of electrons. This is known to us. So central metal ion is placed at the center and it is surrounded by the ligands, and it is very important that the ligand must have one lone pair of electrons. Assumption number 2. The ligands are either negative ions like cyanide ion, chloride ion, or they are neutral molecules like water molecule, ammonia molecule, and they are called as point charges. This is very important assumption. These negative ions or neutral molecules, these are called as point charges. If the ligand is neutral molecule, then the negative end of the dipole is directed towards the metal ion. Assumption number 3. There is no interaction between the metal orbital and ligand orbital. In previous chapter, in valence bond theory, we have discussed that for formation of sigma bond between metal orbital and ligand orbital, there is interaction between metal orbital and ligand orbital. Such type of interaction is not takes place in crystal field theory. Then see assumption number 4. The attraction between the metal ion and the ligand is purely electrostatic, and that is the bond is 100% ionic. That means there is electrostatic force of attraction between metal ion and the ligand, and hence there is formation of ionic bond between them. Assumption number 5. The negative field of ligand repels the electrons of the metal ion, and therefore the metal electrons occupy d orbitals which are away from the ligand orbitals. So what happens? Negative field of ligand, there is repulsion between negative field of ligand and the metal electrons, and therefore what happens? The metal electrons occupy the d orbitals which are away from the ligand orbital. This is for what? To avoid the repulsion. Then see assumption number 6. The number of ligands and their arrangement around the metal ion determine the nature and strength of crystal. Last one. This is very important one. Due to that repulsion, what happens? The degeneracy of d orbitals of free metal ion is removed by the ligands when a complex is formed. In valence bond theory, we have drawn the box diagram of the complex, and in that we have observed that the energy of 5d orbital remains same, remains equivalent. So that is called as degeneracy of d orbital. But in case of crystal field theory, this degeneracy of d orbital is removed. That means energy of 5d orbital not remains same. Got it? So degeneracy of d orbital is removed by the ligands. Then the next point, shapes of d orbital. We know that there are 5 types of d orbital: dxy, dyz, dxz, dyz, dx square minus y square, and dz square. Here we observe that dxy, dxz and dyz, the lobes are in between the axes. while dx square minus y square and dz square, their lobes are along the axis, along z axis, okay, along z axis, along x axis. Hence, there are two types of sets, dx square minus y square and dz square. These orbital form one set and have lobes lying along perpendicular to x, y and z axis. Got it? See here. So these are along the axis. While dxy, dyz, dxz, their lobes are lying pointing between x, y and z axis. See here dxy, the lobes are pointing in between y axis. Okay, here the lobes are pointing in between x and y axis. Here the lobes are pointing between x and z axis. Here they are pointing in between y and z axis. Now see group theoretical symbols. Dx square minus y square and dz square, as the lobes are along the axis, these orbitals are called as EG orbitals. While dxy, dyz, dxz, these orbitals are called as T2G orbitals. E means there are two degenerate orbitals. T means there are three degenerate orbitals. So in this way, this is about 5 types of d orbital which are divided into two groups. EG means along the axis, okay, along x and y axis, along z axis. Got it? And here they are, the lobes are in between the axis x and y, x and z, y and z, and therefore these are called as T2G orbitals. Then see very important point, application of CFT to octahedral complexes. See here, this is the figure, this is the metal. Here there are 6 ligands which are placed along the axis. This is the first ligand placed along z axis, then this is y axis, along x axis, along again z axis, along y axis, along x axis. Ligands are placed along the axis. Got it? And in last slide we have discussed along axis there are EG orbitals, that means dx square minus y square and dz square. And therefore what happened? The repulsion of EG orbitals with this ligand is more, and therefore their energy is increases while the energy of T2G orbital is decreases, because T2G orbitals are pointed in between the axes, and in between the axes okay, there are no ligand. Got it? Here there are no ligand in between the axis, and therefore T2G orbitals are less interacted as compared to EG orbitals, and therefore the energy of EG orbital is increases and the energy of T2 orbital is decreases. So let us see. So in this figure we have observed that metal is at center of octahedron, ligands are at 6 corners of the octahedron. The EG orbitals are directed along the axis and T2G orbitals are in between the axis. The approach of 6 ligands along x, y, z directions increase the repulsion, and hence the energy of EG orbital also increases and the energy of T2G orbital decreases. This is very important. Again I repeat, as EG orbitals are along the axis, ligands are also along the axis, and therefore there is strong interaction between ligand and EG orbital, and therefore their energy is increases. While T2G orbitals are in between the axis, and hence there is no interaction with ligand, and therefore their energy is decreases. Thus, under the influence of an octahedral ligand field, d orbitals split into two groups of different energies which are shown in next figure. See this figure. Here, these are the 5 d orbitals, 1, 2, 3, 4, 5 d orbitals of pre-metal ion. Energy is same. Energy is equivalent. When ligands are approaches toward the metal ion, at that time the energy is increases in this way. 1, 2, 3, 4, 5. This is called as hypothetical symmetrical field. And when Eg orbitals are interacted with a ligand, their energy is increases. So energy of Eg, that means dx square minus y square and dz square, is increases by 6 dq, while the energy of T2g orbitals dxy, dyz, dzx is decreased by minus 4 dq amount. This is called as barycenter. This energy difference between Eg and T2g orbital is called as 10 dq, or it is also called as delta O. O means octahedral. So here this is the d orbital splitting in octahedral field. So this diagram gives information about crystal field splitting in octahedral field. Remember well, the energy of Eg orbitals dx square minus y square dz square is increased by 6 dq amount, while the energy of T2g dxy dyz dxz is decreased by minus 4 dq amount. The total energy difference between Eg and T2g is 10 dq. So the average energy level is called as barycenter. The difference in energy between two sets of T2g orbital and Eg orbital is given by symbol 10 dq. Eg orbitals are 6 dq above average energy level and T2g orbitals are minus 4 dq below average energy level, as we have discussed in last slide. Now see what is strong and weak ligand field splitting. In an octahedral complex, if the value of 10 dq is large, it is called as strong field splitting, and complex is called as strong field complex. 10 dq value is large, 10 dq value is high, at that time it is strong. And in an octahedral complex, if the value of 10 dq is small, it is called as weak field splitting, and complex is called as weak field complex. So strong and weak ligand field splitting is shown in next figure. See this figure. So along this axis, energy is increases. This is again the 5d orbitals of a pre-metal ion. Here when ligand approaches toward metal ion, at that time their energy is increases. Metal ion d orbital energy is increases. This is called a hypothetical symmetrical field. Now see here, this is the difference between Eg and T2g orbital. These are Eg, these are T2g orbital. This difference is 10 dq, value is small, therefore this is called as weak field splitting. See here, this is the energy difference between Eg and T2g. This difference is 10 dq, value is high as compared to this value, and therefore this is called as strong field splitting. Okay, value of 10 dq is larger. It is also called as delta O. This magnitude value of 10 dq depends on the nature of the ligand. Second factor, the charge on the metal ion, and third one, the position of metal in transition series. The ligands which cause small degree of splitting are called as weak ligands. So this is small degree of splitting, therefore they are called as weak ligand. And the ligands which cause large degree of splitting are called as strong ligands. Then see distribution of electrons in d orbital. This is very important. The d electrons are filled in d orbitals by using following rules. Number first, the electrons will occupy the orbital of lowest energy first. We know it. If there are two types of orbital, higher energy orbital, lower energy orbital, so the electrons first enter into lower energy orbital. Second, Hund's rule of maximum multiplicity will be followed. That is, electrons will not pair up unless all degenerate orbitals contain one electron each. That is, they are half-filled. For example, two or if there are three electrons, the first electron goes into 2px, second goes into 2py, third goes into 2pz, but third electron not pair up into 2px, that means 2px to 2py1. This is not the electronic configuration, but the electronic configuration is 2px1, 2py1, 2pz1. Followed? So Hund's rule of maximum multiplicity will be followed. Next rule, if the energy required to occupy the higher energy orbital is greater than the energy required to pair up, which is called as pairing energy, the electron enter in the lower energy orbital. That is, if 10 dq value is greater than p, that means if ligand field is strong, the electron will pair up in the lower energy orbital. If the ligand field is strong, 10 dq value is greater than p, at that time electron will be pair up in lower energy orbital. It not excites, it not enters into higher energy orbital. We are going to discuss in detail with the help of example in next slides. Next rule, if the energy required to occupy the higher energy orbital is less than the energy required to pair up the electron in the lower energy orbital, that is 10 dq is less than p, that means the field is weak, the electron will occupy the higher energy orbital. If 10 dq is less than p, that means if the field is weak, at that time the electron will enter into higher energy orbital. It is not pair up in the lower energy orbital. Then see next rule, the complexes formed by strong ligands contain minimum number of unpaired electrons, and such complexes are called low spin or spin paired complexes. Next one, the complexes formed by weak ligands contains maximum number of unpaired electrons, and such complexes are called as high spin or spin free complexes. We are going to discuss this, what is low spin or high spin complexes, with the help of examples, how the electron are filled and how the complexes are called as low spin complexes or high spin complexes. Let us start. Filling of d1 electron. This d1 electron filling remains the same for both system, for both field, strong and weak field. See here, this is the diagram for both field, strong and weak field. In free metal ion, there is one electron. We are going to discuss d1. The electron remains as it is in hypothetical symmetrical field. Now we have to fill this electron in EG or T2G. We have to follow the rules. So according to rule number 1, the electron first enters into lower energy orbital T2G. Okay, in both field, weak and strong field splitting, what happens? The first electron enters into first orbital of T2G orbital. Hence the electronic configuration is written in this way. One electron is entered into T2G orbital, therefore T2G 1. For one electron, the spin of the electron remains half. So spin for that electron is half. So this is the electronic configuration for D1 electron, and this is the spin. One electron is unpaired for D1 configuration. Then see here, for filling of D2 electrons, in strong and weak field, filling of electron remains same. Along this axis, energy is increases for pre-metal ion. Now see, this is the second electron. There are two electrons in pre-metal ion. Both remain same in a hypothetical symmetrical field. Now we are to fill the electrons in Eg and T2g orbital. As per our discussion, both electrons enter singly in T2g orbital. Here rule number 2 is applied, Hund's rule of maximum multiplicity. There is no pairing of this electron, but instead of that, as the energy is the same, second electron enters into second T2g orbital. This is the filling of D2 electrons in weak and strong field splitting. Hence, electronic configuration is written as T2g2. In T2g orbital, there are two electrons and spin half plus half, it becomes 1. Spin for electron for this field, for strong and weak field, it is 1. So, for strong and weak field, for D2 electron, the electronic configuration is T2g2. Then see, this is for D3. D3 electrons in strong and weak field. Diagram remains same. This is energy increases in this way. In pre-metal ion d orbital, there are 3 electrons, same position in hypothetical symmetrical field. D orbital contains 3 electrons. Now D orbital splits in octahedral field Eg and T2g. Okay. So now third electron occupies third T2g orbital. According to rule number 1, the electrons enters into lower energy orbital. According to rule number 2, Hund's rule of maximum multiplicity, the equal energy orbital consists each electron 1 electron each. There is no pairing of these two electrons. Each electron acquires separate orbitals. So in T2g orbital now there are 3 electrons. No electron in Eg orbital. Weak and strong field splitting. Electronic configuration, we write this electronic configuration in this way, T2g thrice, and spin now becomes half plus half plus half, it becomes 3 by 2. This is the filling of D3 electron in strong and weak field. Next, see now D4 electrons. Filling of D4 electrons in strong and weak field. Here there is a difference in filling of electron in both field. Let us see. Pre-metal ion consists now 4 electron. Same 4 electron remains in hypothetical symmetrical field. D orbital consists 4 electron. Now there is splitting. This is weak field splitting. Eg and T2g. Weak field splitting. 10 dq value is low. And this is strong field splitting. 10 dq value is high. How electrons in weak field enter? See, in weak field, this is first electron, this is second electron, this is third electron. 10 dq value is less, therefore fourth electron enters in above orbital of Eg. So one electron enters into Eg orbital in case of weak field. So for weak field, electronic configuration is T2g3 and Eg1. See this, T2g3 and Eg1. This contains 4 unpaired electrons and therefore this is high spin complex. There are 4 unpaired electrons and therefore it is high spin complex and spin becomes 2. Half into 4, it becomes 2. So in this way this is the spin. This is the electronic configuration for weak field complex. Now there is change in strong field complex. See, out of 4 electron, 3 goes into T2g orbital. 1, 2, 3. Fourth electron is not entered into Eg orbital, but it pair up into T2g orbital because 10 dq value is higher. Fourth electron is not able to enter into Eg orbital because 10 dq value is high. Field is strong. There is pairing of first electron. This is the difference in filling of electron in weak and strong field splitting. And for strong field splitting, electronic configuration is T2G4. All electrons are filled in T2G orbital, and this contains only two unpaired electrons, and therefore this is low spin complex and spin is 1. Followed? Spin is 1. This is about the filling of d4 electrons. Then see d5 electrons. For d5 electrons, what happens? In strong and weak field, there is a difference in filling of electron. Let us start. Free metal ion consists 5 electrons. 1, 2, 3, 4, 5. In a hypothetical symmetrical field, the position of electron remains same. Okay, so d orbital contains 5 unpaired electron, and now in octahedral field, in two field, this is the weak field splitting, this is the strong field splitting. Here 10 dq value is high, here 10 dq value is low. Therefore in weak field what happened? 3 electrons enters into T2G orbital and 2 electrons enter into EG orbital. Hence the electronic configuration for weak field is T2G3 EG2. So there are 3 electrons in T2G orbital, 2 electrons in EG orbital, and hence this contains 5 unpaired electrons. Hence this is high spin complex and spin is 5 by 2. Now see, in case of strong field, as 10 dq value is high, electrons are not able to enter into EG orbital, hence there is pairing of these two electrons. Okay, so 1, 2, 3, fourth electron is paired and fifth electron is paired with these two electrons. Hence electronic configuration in strong field complex is T2G5, and this contains only one unpaired electron. See, this is the only one unpaired electron. This is called as low spin complex, and spin is given as low spin split. This is called as low spin complex because there is only one unpaired electron. Friends, we stop here, and in next lecture again we discuss the filling of next d electron, d6, d7, d8, d9, d10 electron in strong and weak field. Thank you.